Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisens and responsible for production and development of Unisens microsensors. In this presentation I will give you an introduction to how our nitrous oxide microsensors are designed and working, which hopefully will familiarize with them and help you in applying them correctly. The Unisens nitrous oxide microsensor is of the amperemetric microsensor type, also known as Clark type sensors, and a detailed web lecture about the working principles for these sensors is available on our website. So this lecture will focus especially on the nitrous oxide microsensor and its performance. It will cover the following topics: tip design and detecting principle, the specifications, I will give some comments to them. Then I will show how our needle sensors are made, and at last there will be a troubleshooting section. So here you see a nitrous oxide sensor and the tip of it in action. Details and theory about Unisens amperemetric microsensors are covered in the lecture about Unisens amperemetric microsensors, but I will here describe the tip design and working principle of the nitrous oxide microsensor. The nitrous oxide microsensor detection principle is patented. It consists of a nitrous oxide sensitive amperemetric microsensor which is built like other Unisens amperemetric microsensors, with a glass casing equipped with a silicon membrane, working electrode, reference electrode, guard electrode and electrolyte. The negatively polarized working electrode is made of indium, which has a nitrous oxide reduction catalytic property. The electrolyte consists of an organic solvent containing a suitable salt, ensuring electrical contact between electrodes and charge balance. The guard electrode uses oxygen and other dissolved substances dissolved in the electrolyte, which would otherwise react on the working electrode. So the guard electrode keeps the baseline low. The reference is a silver wire. The nitrous oxide microsensor is built into a second tapered glass casing, also equipped with a silicon membrane, and this is the front guard. It contains an oxygen scavenging solution consisting of an alkaline sodium ascorbate solution, which is a strong antioxidant. This solution reduces oxygen, which would otherwise interfere with the nitrous oxide measurements because oxygen is readily reduced on the indium working electrode. The membrane is permeable to nitrous oxide. If nitrous oxide is present, it diffuses through the membranes and the scavenging solution to the working electrode. The working electrode surface is a negatively polarized indium electrode which catalyzes reduction of nitrous oxide. The electrons for the reduction are delivered from a silver reference electrode 10 cm away from the working electrode, but for sake of illustrating the principles, it is included in the schematic drawing of the tip. The current generated is proportional to the concentration of nitrous oxide outside the tip membrane, and as the current is very small, in the picoampere range, a high-quality amperemeter is necessary for amplifying such tiny current. The indium working electrode reduces nitrous oxide efficiently in the organic electrolyte, but only if the surface is reduced. A layer of indium is formed when the working electrode is not negatively polarized. This layer makes the working electrode completely inactive to nitrous oxide reduction. Therefore, this oxide layer must be removed in an initial activation process. This is done by applying a high negative polarization for about 30 minutes, which reduces the indium surface. This graph illustrates the signal from a nitrous oxide sensor during the time of pre-activation. Right after turning the polarization to minus 1.3 volt, the signal starts rising due to the reduction current and could reach an out-of-range current. After some minutes, the current starts to decline to some 100 picoamps, and after 30 minutes, the polarization is adjusted to minus 0.8 volt. The baseline goes down and will stabilize on a low level, typically below 10 picoamps. This pre-activation must always be carried out when connected to a Unisens amplifier if the sensor has not been used within a few hours. The working electrode surface will start to become oxidized when removed from the amplifier and thus depolarized. I will now turn to the actual performance and specs of the nitrous oxide sensors and give some comments to them. Recall that these specs are only guaranteed with use of a Unisense meter. The limit of detection is stated to be 0.1 micromolar dissolved nitrous oxide. However, the detection limit is strongly influenced by the application in question. The smallest version have a higher detection limit due to the small current generated. The largest version can be made with the larger chip membranes, achieving a detection limit down to 25 nanomoles in a low-range version. The standard chip size ranges from 50 to 500 micrometers. We produce them in standard models with 50, 100 and 500 micrometer chips. We can, however, make them with chips down to 20 to 30 micrometer. Naturally, the smaller the chip is, the more fragile it will be. Larger sensors are made with thick glass walls, making them quite robust for profiling in matrices like sediments. Compared to other Unisense amperemetric microsensors, they have wider membranes, making them somewhat more vulnerable to membrane damages when profiling in matrices. We can to some extent custom make the chip design regarding slenderness and modify the body if requested, but the two casing design limits the possibilities. The response time is a function of the nitrous oxide diffusion path link into the working electrode, and the diffusion path through the front guard makes it slower responding compared to other Unisense amperemetric microsensors. The smallest sensors are made with a shorter response time, less than 20 seconds, whereas the larger and more robust versions have up to 45 seconds response time. Details on response time is found on our website. The nitrous oxide sensors respond linearly to nitrous oxide concentration at the sensor tip. It will respond linearly up to quite high concentrations, but we do not recommend to use standard nitrous oxide sensors in concentration higher than 500 micromolar. Nitrous oxide is reduced to dinitrogen, which will be dissolved in the electrolyte. When measuring in high concentrations of nitrous oxide, the rate of dinitrogen production at the working electrode is high and can saturate the tip electrolyte with dinitrogen, which potentially forms a dinitrogen gas bubble. Such bubble will disconnect working electrode from the reference, and the sensor does not anymore respond to nitrous oxide. Thus, sensors which are produced to measure concentrations in the millimolar range must have a reduced sensitivity. This is done by reducing the diameter of the chip membrane. We can custom make sensors to measure in saturated nitrous oxide solutions. The spatial resolution equals the tip diameter. This is just a rule of thumb because it cannot easily be validated. The sensor will sample nitrous oxide from a very minute diffusion sphere at the membrane/sample interface. But when profiling in biologically active matrices, physical disturbances should also be considered, which increase with chip size. The sensitivity to steering is for standard sensors less than 1%. The sensitivity to steering is defined as the difference between the signal in stirred and stagnant samples with the same nitrous oxide concentration. This is exemplified here, where a sensor measures in a continuously mixed sample. When the steering is stopped, the signal decreases about 1%, which is typical for a nitrous oxide sensor, and when the steering is reactivated, the signal is back to the original level. The lifetime of a nitrous oxide sensor is determined by the lifetime of the membranes. The silicon membranes are slowly deteriorated by the alkaline front guard solution. We have without success searched for a less membrane aggressive solution with the same oxygen scavenging efficiency, but so far without success. The longer the membranes are, the longer the lifetime will therefore be. And for long-term monitoring, our N2O sensor is made with long membranes. This gives an expected lifetime of 6 to 8 months. The downside is a slow response, up to 45 seconds. The version we sell for wastewater monitoring is sold via our sister company, Unisense Environment, and this is made with similar long membranes. The lifetime is not dependent on how much it is used, it is simply a function of time. The profiling sensors with a faster response time have short membranes and therefore an expected lifetime of no more than 3 to 4 months. Nitrous oxide sensors are among the most stable sensors I know of. Typically, the signal does not drift more than 20% in the lifespan of the sensor, so the weekly to monthly drift is minimal. The baseline does not change significantly with time. Physical impact to the sensor can, besides destroying the sensor, change the sensitivity and thereby the calibration curve of a nitrous oxide microsensor. The working electrode connects to the amperemeter via a thin, flexible glass-covered platinum wire. Physical impact, which shocks the internal components, can induce a displacement of the working electrode position relative to the membrane, thereby changing the sensitivity. Typically, such impact will induce a sudden signal peak followed by a stabilization time, but the sensitivity might not return to the original sensitivity caused by a displacement of the working electrode position. The baseline is typically not affected. Nitrous oxide sensors stand up to 3 to 5 times atmospheric pressure without being pressure compensated. Due to the design constraints, it is not possible for us to pressure compensate the sensor, and therefore we cannot supply nitrous oxide sensors for deep sea applications. In the web lecture about amperemetric microsensors, the temperature influence is discussed in details, and it is explained why temperature compensation is difficult for amperemetric microsensors. The temperature interference is about 2% per degree. For sensors used with a new uniamp portfolio, temperature is compensated for within a plus minus 3 degrees Celsius interval. The sensors can be used from minus 10 to 50 degrees Celsius. At higher temperatures, the baseline and noise level increases and compromise the sensitivity. I will not in this presentation go into details with all the adaptations and modifications we can do to the nitrous oxide sensor. This is covered in the quick guide, but I would at this point describe how a needle-embedded sensor is made. Due to the complicated design, we only make needle-embedded nitrous oxide sensors in a 1.6 mm needle, the N2O NP. It is designed so it stands penetration of membranes. This is a schematic drawing of the tip of a nitrous oxide NP sensor. The needle protects to some extent the glass and membrane, but the sensor tip is still fully exposed to the sample solution. The needle and the glass part of the sensor are glued together inside the needle, so no sample liquid will intrude into the needle. This would otherwise result in a huge carryover effect. I now turn to troubleshooting nitrous oxide microsensors which do not exhibit normal performance. A broken sensor will in water give a very high signal, typically out of range, as the polarized working electrode is directly exposed to the sample. So if the tip breaks during measurements, a sharp signal rise will occur to the out of range signal. If only the front guard glass casing and membrane are damaged, it might still be responsive to nitrous oxide, but will be sensitive to oxygen. Oxygen interferes strongly, and thus a large signal will be generated in oxygen-containing samples or in air. If the signal is low and stable in anoxic samples close to the baseline, but unstable and high exposed to oxygen, the outer glass casing, glass or membrane is most likely damaged. It is not possible to repair a broken sensor or replace the outer casing. If the sensor tip gets biofouled or covered with sticky polymers, it might measure incorrectly. The tip tolerates almost all possible cleaning substances like alcohol, acids, detergents, proteinase solutions, etc. So it is recommended to insert the sensor into different cleaning solutions to see if this solves the problem as the first attempt to remove the fouling. If chemical cleaning does not remove the fouling and restore normal performance of the sensor, a physical cleaning is the only solution. If you hold the sensor tip so it points away from you, the wipe direction must always be the direction the tip points, never against the tip, which will impose a risk of tip damage. I showed before how the signal progresses during the pre-activation phase. If there is no signal rise when polarization is turned up to 1.3 volt or minus 1.3 volt, but instead stays close to zero, it might be due to a gas bubble stuck in the tip, which disconnects the working electrode from the reference. There must be an air/gas phase in the electrolyte cavity in order to make room for temperature-induced expansion of the electrolyte. And if the sensor package was turned upside down during shipment, a gas bubble can be trapped in the tip. Such gas bubble can be removed by shaking the sensor like it is demonstrated here. The bubble will become loose and rise to the top of the electrolyte cavity, and connection will be restored. If the sensor is sensitive to oxygen and it is for sure not physically damaged, potentially it could be due to a gas phase in the front guard tip, which will cause oxygen to diffuse to the nitrous oxide sensor tip membrane. Such gas phase can easily be removed by inserting the tip into degassed water, which will drag the gas out of the tip through the membrane. Fill water into a glass bottle and boil the water. This drags gases out of the water. Let the water cool to room temperature or below without shaking the bottle or mixing the water. Place the sensor tip into the water for some hours. The gas will be removed by this procedure. If a sensor experiences a physical impact, like a drop on the table, the working electrode could be displaced. If the displacement results in a working electrode retraction from the silicon membrane, the signal will be slow and sensitivity low. The sensor will still work, but it will have lost its original behavior. It is unfortunately not possible to restore original performance after such an event. A physical impact, like a drop, could also damage the glass insulation of the platinum wire connection to the working electrode. This will typically result in an elevated and noisy baseline signal due to exposure of polarized platinum to the electrolyte. Chemical reaction taking place on the exposed platinum surface will create a current which will overlay the working electrode generated current. The size of the baseline increase will depend on the degree of damage to the platinum wire insulation. Such damage can not be repaired either. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.